All right, welcome back today for our second video. We're going to be talking about gas stoichiometry. First of all, the STP conditions we are not going to go over because you have already done these. When we went over our unit on stoichiometry, you covered this in great detail. When we went over the fact that 1 mole of any gas at STP will occupy 22.4 liters. So you can go back to your stoichiometry unit for all of your sample problems covering that. Those would be the same stoichiometry sample problems that would involve any volume stoich problems. So anywhere where you used 1 mole equals 22.4 liters. So when would you know to use this? Whenever it says a gas at STP. So when do you not use this? Well, whenever we're talking about a gas and the conditions of STP are not mentioned. So they won't say this gas is not at STP. They just won't say they are at STP. And so when they don't say that they're at STP, then you assume that they are not at STP. And so when that happens, you have to use a combination of stoichiometry and the ideal gas law. And then you also must realize that you're going to have to write a balanced chemical equation. Why? Because you're going to need to use your mole ratio for your stoichiometry. So the combination of stoichiometry and the ideal gas law, sometimes you'll use the stoichiometry first and then the ideal gas law, and sometimes you'll use the ideal gas law first and then the stoichiometry. You really have to look at what you're being given and what you have enough information to use. If you have enough information to use the ideal gas law to get to moles, then you'll use the ideal gas law first. If you have enough information to get to moles from your stoichiometry, then you'll start with your stoichiometry. So I'm going to go through that with our sample calculations to kind of help guide you through this. So our first sample problem is how much pressure in kPa would be exerted by a gas produced from 10.5 grams of magnesium reacting with an excess of hydrochloric acid if it is collected at 35, that should be a small, degrees Celsius in a rigid 5.0 liter container. So the first thing we're going to do is write a balanced equation to kind of get a better picture of what's going on. So we have magnesium reacting with hydrochloric acid. And hopefully you look at this and go, oh, that is a single replacement reaction. Magnesium is going to try and kick out hydrogen. So you look at your activity series, and magnesium can kick out hydrogen. Or maybe you remember this from our lab that we did, because you put magnesium into the test tube with the hydrochloric acid. And you know that this would occur. Magnesium kicks out hydrogen gas and forms magnesium chloride. Magnesium is +2, chlorine is -1, and then hydrogen by itself is a diatomic element. When we balance this, we end up with a 2 in front of the HCl, and so this is our balanced equation. They give us 10.5 grams of magnesium. And then they say how much pressure would be exerted by a gas produced. Well, which one of our products is a gas? And that should be pretty easy to figure out. That hydrogen is the only product that is a gas. They wouldn't be able to ask us this question if both of the products were gases. So it must be that only one of our products is a gas. And so if we're collecting this gas and they tell us that it's at 35 degrees Celsius, it's in a 5.0 liter rigid container, and they're asking us the pressure of this gas. Well, that means we know the T, we know the V, and they're asking us again the P. Well, if they're asking us the P, that means somehow we must need to know the N. And they want the P in kPa, so that means the R that we're going to use is 8.31, because that's the one that matches with kPa. So right now we can't use the ideal gas law yet because we don't know N. We'd have to know N in order to solve for P, because right now we have two unknown variables in our ideal gas law. So right now I know that I'm going to have to first use Stoich, then I'm going to have to use PV equals nRT. Because I'm going to have to use Stoich to get to moles, and then moles I'm going to use in my PV equals nRT. All right, so that means I'm going to use Stoich to get to moles of my gas. So this is going to be just a regular stoichiometry problem. I'm going to go from my 10.5 grams that they give me of magnesium, grams of magnesium. I need to go to moles of magnesium. I look on my periodic table, and I believe there's 24.31 grams of magnesium in 1 mole of magnesium. And then, according to my mole ratio between magnesium and hydrogen, it's a 1-to-1 mole ratio. Moles of magnesium go on the bottom, and moles of hydrogen go on the top. I only have to go to moles because that's all I need for my ideal gas law. I solve for this and I get 0.432 moles of hydrogen, which is my gas. I plug that in. Then I use my PV equals nRT. P is my unknown. V is 5.0 liters. N, we just found out, is 0.432. R is 8.31. T, I got to plug in and make it in K, which I add 273, which makes it 308. And I end up with a pressure of 221 kPa. All right, the next one. How many grams of calcium carbonate would need to decompose? Well, that's a metal carbonate. If you remember your special cases, metal carbonates decompose into metal oxides and carbon dioxide, which, by the way, is my only gas. That's going to be important. And it's decomposing at 20 degrees Celsius in order to produce enough carbon dioxide to fill a 500 milliliter container at 0.950 atmospheres of pressure. So let's think about my gas here. I know its temperature is 20 degrees Celsius, which is 293 K. Its volume, I'm going to just go ahead and move my decimal over because I know it has to be in liters. So that's 0.5000 liters. Its pressure is 0.950 atmospheres. Because pressure is in atmospheres, I know I can use an R that matches atmospheres, which is 0.0821. And now I have everything, so I can solve for N. And they're asking me for the grams of my calcium carbonate. So this problem is opposite my previous problem. So in this problem, I'm not going to start off with Stoich. I'm going to start off with my ideal gas law. And then I'm going to do my stoichiometry after that. So I'm going to do ideal gas law to get moles, and then I'm going to use my moles to do my stoichiometry. So I'm going to do my ideal gas law, PV equals nRT. My P is 0.950. My V is 0.5000. Remember, I converted my 500 milliliters into liters. I'm leaving my N as is. That's what I'm solving for. My R is 0.0821 to match my R value with my pressure. My T is 293 because I have to have it in Kelvin. N, then when I solve for N, I take 0.950 times 0.5000 divided by 0.0821 divided by 293. And I get an N value of, let me check that again, 0.95 times 0.5 divided by 0.0821 divided by 293. And I get 0.0197 moles of carbon dioxide. Then I take my 0.0197 moles of CO2, and I know my mole ratio, because it was already balanced, is 1 mole of CO2 for every 1 mole of CaCO3. And then they don't want moles of CaCO3, they want grams. And so I do a molar mass, and that molar mass is 100.09 grams of CaCO3. And my final answer is 0.0197 times 100.09 is 1.97 grams of calcium carbonate. All right. Please, as always, let me know if you have any questions. Work these out slowly and meticulously. Make sure you have a good balanced equation. And double check your answers.